This time we have 4 people, but typically we have 6, 7. Yeah. So welcome everyone to Applied and Computational Math Seminar. Welcome to people on Zoom as well. I think you can see me and I'm speaking to the microphone. So this week we have Tom Barker as the speaker, who's recently joined the department as a lecturer. And as I checked just before coming here, Tom did his PhD in Manchester with Nico Gray, who was the speaker a few weeks ago. He then did a postdoc at Manchester as well, followed by a postdoc in Edinburgh. And now he's here and he'll be talking about using well-posedness to guide rheological modeling. So Tom, over to you.
Excellent, thanks Maciek. And yeah, great to see you all here today. And it's quite a nice novelty doing an in-person talk. It's been such a long time. I don't even know how many months since the last time I did anything in person. But yeah, this is kind of what I did during my PhD actually in Manchester. But I kind of thought I'd talk about this today because I think it's quite generally relevant to lots of areas, hopefully, in applied math. And it'd be cool to see if any of you can spot areas of your work which could benefit from some of these methods. And normally I give kind of an overview of these concepts and the applications, but I'll go into some more like specifics and go through some of the details for a couple of examples today. And so the concept is talking about the difference between well-posed and ill-posed PDEs. So I can probably take my mask off actually, can't I? So yeah, so what's the idea? So we're looking at perturbations, we're looking at doing a stability analysis of the PDEs. I think there's something going on with my
it's going really quick.
Yeah, yeah, sorry. Is it automatically going through? Let's leave the mouse on the table and see how we go. So we're looking at the behavior of perturbations in general, okay? But for this special situation, we're looking at the high wave number limit, okay? And so that allows us always to look for these nice normal mode solutions, look like these exponential forms here, quantified by some, characterized by some wave vector k and some growth rate in time lambda. Okay, and so this is, you know, kind of bread and butter stuff. On the right, you can see some examples of some very typical dispersion relations. The green curve, all the different modes, all the different wave numbers, all the wave vectors are all decaying. In the blue case, this is maybe what you'd find in wave-like phenomena. You've got some modes that are growing and then some modes that are decaying. And you've got some kind of like maximal growth rate at some quite long wavelength. So you can think this direction's long waves and this direction's short waves. And so that would be a typical water waves or something where really tiny ripples, they decay away, but then you've got these bigger long wavelength modes that come to dominate. The black curve here is a bit more tricky to understand, like all the modes are being amplified above a certain amount. It's kind of plateauing, but you can imagine this could be describing a kind of shock phenomena where you've got a very discontinuous jump in a quantity, and you can think of all these modes as kind of Fourier modes. In order to resolve something with like sharp edges, you would need infinitely many different modes to resolve that. But the thing we're really going to be worried about today are things where the dispersion relation looks like this red curve. So as the wave vector gets really large, so the wavelength is getting smaller and smaller and smaller, the growth rate is getting bigger and bigger. And so the way I describe this to the physicists is if you're doing an experiment in your lab and somewhere in the building, a very high frequency alarm is going off, that's high frequency noise and it's really low amplitude, you don't expect that influence to come and dominate your experiments. In fact, you don't expect definitely your experiment to blow up because there's this tiny disturbance happening. Okay, so this is a kind of very unphysical type of dispersion relation. And as I say, we're only going to be worried about what happens in this very high wave number limit. And we don't really mind if it does something different in the low, in the long wave limit. Okay, so as I said, this is a kind of general way of looking at solutions of all different types of PDEs, but today I'll limit attention to kind of the bread and butter of a lot of continuum mechanics, and in particular looking at material deformations. And so we've got mass conservation and momentum balance. So two different PDEs coming from physical laws. Of course, you could have other conserved quantities as well as mass, and you could have other variables floating around that might couple and influence some of these fields. But the big kind of art, if you will, or the area of most research in continuum mechanics is developing closure relations, developing constitutive models for this Cauchy stress tensor sigma. Okay, and so you may also have some body forces around. But the question is, can we help ourselves in this kind of wide open like art of developing models for sigma by using this concept of ill-posedness and well-posedness? Okay, so this is the first example I'm going to present. This is a model for granular flow. And in this model, known as the incompressible mu of I rheology, this was developed by physicists thinking about a kind of schematic picture of a really simple, and physicists often do this, start with spheres in a vacuum. And in fact, actually, we're going to focus today on just two-dimensional flow. So it's circular particles in a vacuum, in a shear flow, in some sort of boundaryless problem to start with. Of course, you can think of any like non-linear varying flow. If you zoom in closely enough, you can decompose that into these linear segments of shearing. But in any case, the physicists looked at this picture and said, well, what are the quantities of interest that we'd like to put into the modeling? Well, we want to know a bit about the bulk response, and this has been known for a long time. If you take the ratio of the shear stress, and that could either be an implied shear stress, or it could be the response of I'm shearing the material, how much is it rubbing, you know, Newton's third law. But yeah, you got the shear stress tau and some pressure P, some isotropic component of the full stress tensor. Take the ratio of those two and you've got a bulk friction. So this goes back to like Coulomb, thinking about friction on surfaces. This is a generalization to in this case, 2D. And then the other quantity that started to become really quite important to these guys when they saw a really nice collapse was a non-dimensional strain rate. And so there's lots of ways you can non-dimensionalize the strain rate, but they found really nice collapse using this inertial number. Okay, so that brings in information about the particle scale through the grain diameter D, through the density of the grains themselves, rho star, and the pressure. So it's kind of coupling together in a way these kinematic variables to the stress variables. And so yeah, they focused on these two non-dimensional numbers. If you've got two non-dimensional groupings that you think specify your system completely, one of them is going to be a function of the other. And so that's why it's the mu of I rheology. And then the big assumption they made is that the flow is incompressible. So the amount of empty space doesn't change, and the amount of grains doesn't change, and your velocity fields are therefore incompressible, divergence free. Okay, so combining all these ideas, you can construct now the full stress tensor as a closure to those Cauchy momentum balance equations. And it looks like this. So you got, as usual, you've got an isotropic part coming from just the pressure. In these systems, the pressure is just a response to incompressibility. And then you've got this mu of I rheology controlling the shear stress part. And so mu of I times P is like the magnitude of the shear stress. And then the idea is that you align your direction along which the shear stress is maximal with the direction along which the strain rate is maximal. Okay, so the direction you're deforming is going to also be the direction you've got the most resistance to flow. And so that's the idea of alignment. Okay, so let's see how this all fits together. Yeah. Sorry? Oh yeah, that was to represent the pressure. So if these surfaces are where the shear is happening, these surfaces would also be experiencing some outward force from the pressure of the grains as well. It could be, it'll be both, right? Of course. In this definition of the pressure, it would be outwards. Yeah. Okay, So substitute that new stress tensor form into our full equations, and we get this system. I'm going to kind of switch back and forth between kind of vector tensor, bold notation, and component-wise at different points. I hope it's not too disorientating. So yeah, so 9 is again our incompressibility constraint. This was the big assumption that was made. Number 10 here is now the momentum balance equations, right? You've got acceleration on the left-hand side, and then you've got these new dissipative terms, right? You got this gradient of pressure and any body forces that might be acting on the system. And the nice thing about this is a direct analogy now is quite clear with the kind of classic Navier-Stokes equations describing liquid flow, describing Newtonian fluid flow, and that's if you define some variable viscosity. So we look at this term and think, well, it looks like Navier-Stokes, except for the fact that you've got all this extra dependence. So it's kind of quite involved dependence in pressure, strain rate, that both go into the inertial number as well. And so it will depend on the functional form of mu, how it depends on I, exactly, you know, how all the nonlinearity in that variation comes about. And so that's what we're going to be kind of trying to tease out of the equations. What real implications are there to this now varying viscosity with those particular dependencies? So we go back to this idea of ill-posedness and well-posedness, and we start by looking at just general perturbations now, where the perturbations are of order epsilon. And so we're looking at early times, we're looking at small amplitudes. We'll just do a linearization, keeping only order epsilon terms. But then we've got this extra step, step 3, because we're only going to be worried about what's happening in the high wave number limit. And we know that any gradients in our model are going to be bringing down the wave numbers, you know, e to the ikx differentiate with respect to x, you're going to start getting some k terms, right? And so to make our lives easier, before we even think about those normal mode solutions, we can identify what's called the principal part of the PDE. And that is only the highest order gradient in each field, in each equation, with respect to each variable. So if I've got a first order derivative in time of velocity and a second order derivative in space, I keep those two, but I would not keep a first order in space. Okay, so we're kind of like counting the fields, the variables, and the gradients. So for this mu of I rheology, the real hard work is all going to come from this new term, right? All the other terms are quite trivial, but this term has got all these kind of hidden dependencies as well. And so you have to do a lot of product rule, a lot of chain rule to bring out all the gradients of velocities and pressure. So we've got kind of 3 fields here. We've got the 2 velocity components in 2D and the pressure, and our 3 equations, incompressibility, and the 2 mass balances. And so yeah, so we do all that and keeping only the highest order gradients. For the incompressibility, that's pretty straightforward. There's only one gradient there. There's only going to be one gradient in the answer. For equation 16, you see on the left-hand side, we've just kept that time derivative. That was the only time derivative we had, so that's going to be kept. That's the highest order time derivative of the velocity in our equations. On the right-hand side, we've got quite a few things going on. You can see the first term on the right-hand side is second order gradients of the velocity, and the second term on the right-hand side is first order spatial gradients of the pressure. And so they're all the ones that survived. You know, and then there's all these kind of groupings that we made that I'll kind of go through now, explain where all of those came from. So we found it was quite convenient to group together the strain rate tensor in the base state, normalized by its magnitude. So we've got kind of this director tensor now telling us in which direction the principal axis of the strain rate is relative to our coordinates. And to start with, our coordinates are quite arbitrary, but in any case, so that's kind of a director tensor scaling certain components. So certain ones of these components are going to care about what direction the perturbations are relative to the base flow. And so the thing about doing this principal part analysis, this well-posedness analysis, because the frequency is so high, we can really zoom right into the flow, and everywhere relative to the perturbations, the background flow is a constant. And so all these things, these A's, R's, Q's, are all just constants. It's like a frozen coefficient system. And so all the zeros here are just evaluate with respect to the background field. So yeah, so the next term we can see is that we've got this A to 0 scaling all these terms. And this is nothing but the non-constant viscosity evaluated with the base state fields. And so this is something you'd expect and something you'd see in Navier-Stokes as well. Like viscous terms are going to be, scaling the dissipation of the perturbations as well as the flow fields. But the really kind of intriguing aspect, and what links into the idea with my talk about guiding the development of the rheological models, is that these terms R and Q, they depend on the value of mu, the value of I, but also the gradient d mu by di, so the shape of the mu of I curve. And so this is kind of suggesting that this analysis is going to give us a recipe for cooking up different shapes of mu of I curve, different dependencies in the rheology to control the stability of these high wave number modes. Okay, so as I said, we've done the principal part, and that really helped us have a simple system. Substitute in our normal modes. We've got constant coefficient equations, so the normal modes are solutions there. You may be thinking, oh, well, in normal stability analysis, we've got to consider the boundary conditions as well. Again, because we're doing these high wave number modes, we're zoomed right in on the base flow. It doesn't matter how close you are to the boundary, you don't need to worry about those conditions. So these modes are always permissible in this kind of infinitely small scale limit. Okay, so that was quite straightforward. All the gradient terms I had, all the derivatives, they're just bringing down different wave numbers. So where I had a d by dj, I've now got a kj, etc. But the real thing to now do is combine this all. We've got at the minute three equations actually, for three unknowns. So we got the two velocities and the pressure. And so that is kind of like quite an awkward system to work with, especially it's split in this way. So what we did is actually solve this equation 21 for the pressure, provided that we know this equation 20. And so we're reducing the number of unknowns by solving for what the pressure perturbation is, just by the fact that we know that, in fact, equation 20, you can see it's the dot product of the wave vector with the velocity. If the dot product is 0, they have to be perpendicular. And in 2D, there's just a unique perpendicular vector, right? So we just said all the eigenvectors of velocity perturbations must also be parallel to the wave vector. So that helped really simplify things, gives us just a single now eigenvalue problem. Okay, so grouping all these terms into an operator now, acting on the velocity perturbations. And that can be solved then directly to find a full now expression for the growth rate as a function of the wave vector. And so this is like going to depend on the actual magnitude of the wave vector, the direction of the wave vector. And remember, this A was like the direction of the principal axis of the straining, the underlying strain rate field. And so this is kind of looking a bit complicated, but we made some nice gains by considering, the order of everything and the sign of everything. We noticed that everything in the denominator was positive. This Q actually turned out to be less than 1. All the terms in the top scale like k to the power 4. Everything in the bottom scales like k squared. So overall, you've got a quadratic. So it's either quadratic increasing or quadratic decreasing. And so we can kind of not worry too much about the maybe complicated structure of that expression and focus instead just on the numerator. And so again, we've got these strain direction tensor, as well as all the different wave vectors, and we're trying to analyze the stability of it. Can be quite complicated. We've got to consider all the possibilities, but we realize as well, because we're in this local frame, it should be rotation invariant. We should be able to choose any rotated value of this underlying strain direction, and it shouldn't affect the stability. It will affect the directions at which we've got the fastest growing modes, but it won't affect whether the modes exist in the first place and how fast they're growing. Okay, and so we chose a specific value, a specific form of this A tensor that made the maths as easy as possible, and that gave us this quartic now where the argument is K1 over K2, some direction in our Fourier directed space. So everything comes down to the sign now of this n tilde. And all I really need to know is if there are any roots. It's a quadratic equation. This is K4, this is K squared. You know, technically a quartic, fourfold symmetry. Let's just make it into a quadratic by substitution. So it's a quadratic equation. Has it got any roots? We just need to analyze the determinant, right? So I take the determinant of all of this quadratic and ask if that's greater than 0. If it is, I've got some roots. Part of my quadratic is going to be positive, and so I'm going to have some regions, some directions, which give positive growth. Okay, so let's see how that all falls out. Remember, those R and Q terms were the ones I was kind of interested in, because they have d mu by di, they have mu in there, they have I in there, and when you substitute all that in, you get this kind of global condition on well-posedness. Actually, it's ill-posedness in this case. If this thing on the left-hand side is greater than 0, then we're going to have these positive unbounded growth rates. So we went back to the literature and looked at what functional forms they usually use for mu of I, and this was a kind of gold standard at the time that had been well justified by experiments, starting from some low value, some static value when I is 0, and coming up and asymptoting some higher value when the inertial number is really large. Okay, and so we just substitute this form and the parameters that were being used in the literature into our condition and see what happens. And so we found that the region of parameter space, the region of inertial numbers, where the majority of the experiments were being done, was actually leading to well-posedness, well, at least linear well-posedness. Okay, and so that was kind of nice in a way, but we still weren't fully happy because we found these other regions. So when the inertial number was quite large, this condition was satisfied. There's also this region of small inertial numbers, easier to see on a logarithmic axis, that was also going to give us ill-posed dynamic equations. And the issue here is, when you want to consider a real flow in nature or in industry, you're pretty much always going to have some region of the flow which is almost static, and some region maybe is very highly agitated, and you really want your model to be able to go at least all the way down to I0 and to at least some reasonably large value of the inertial number. And the guys who designed this kind of already knew probably different physics happens in those regions. So that was kind of a nice realization from our end as well. So we took those equations, and just to make sure that the physicists who designed this weren't thinking we were, making it up completely, we went and solved those raw mu of I equations numerically in 2D to see what would happen when the inertial number was either in this very low ill-posed range or the very high ill-posed range. And so both of these are done for inclined chute flows on an inclined plane. At the left-hand side, we took a flow at steady state and then decreased the angle. So the flow was decelerating, meaning that the bottom started to freeze, started to slow down. And we saw all these funky perturbations in there forming spontaneously. In fact, the top panel A was done on quite a coarse numerical mesh. And on the bottom panel B, we did it in an even finer mesh. And so you can see that the kind of modes that are able to be resolved by the numerics really is going to change the output of the solution. In other words, we got grid dependence. We also found that these modes grew faster and they generally saturate at a higher level. Of course, once they grow, it becomes a kind of non-linear problem, and probably these growth rates, well, they definitely get cut off by some other effects. And in the high angle case, a very large inertial number, where the exact solution in this situation, the exact steady solution, should I say, would be a uniform value of the inertial number. I think it was around 0.6. But as you can see, again, these spontaneous formation of perturbations, in this case, they've kind of all evolved and coarsened and rolled over through some wave vector stretching, exciting physics. But in any case, we still think this is very unphysical because, you know, it still depends on the grid resolution and the numerical method you use to solve the equations. So it'd be really a nice thing to get away from. So one idea was to go back to that condition of ill-posedness, and instead of asking when am I ill-posed, when am I well-posed, ask instead, what is the neutral stability? What is the turning point between those? What defines that? And then my idea was, well, the mu of I curve that the physicists had cooked up was really good in that middle region. It was fitting the experiments really well. So let's trust that all the way to the edge until we become ill-posed, and use that then as a boundary condition. Remember, we've got d mu by di terms in here. So really you can think this equation 28 is like an ODE for mu as a function of I. And so I used just their value at the edge when we first become ill-posed as a boundary condition and solve. And it turns out there's two solutions, and you can see them here. And so they define the edges of this region. Inside that region, it means I could make some well-posed curves. It doesn't mean that all curves are well-posed, but you know, if I was very close to the edge and I had a similar functional form, I'm probably always going to be fine because I'm very close to neutral stability and I'm just on the inside. And so we think this IN minus, one of the branches, is probably a lot more realistic. We're probably not going to come in and then suddenly, you know, dive down to the origin. But, you know, this was just a theoretical analysis. The same with the large inertial numbers. We've got these two branches, we've got this region. In fact, we found there was like a maximum value of mu and of I, above which you really can't make any curves, which would make this equal to 0. And so these run out at these special values, which is still quite odd, but we're actually up to now, inertial numbers are like 100 or something, which the physicists will say, yeah, it's never going to happen. If you get up to I is 1 or 2, then you're already very gaseous and completely different physics. So it's just a bit of an oddity of the analysis, I guess. But yeah, so recently I've been doing some other flows, looking at other systems. And so here is a granular flow down a vertical chute. And so we've got these black kind of ghost-like particles confining the flow, and then just gravity pointing down, and everything flows down, but you got no slip at the walls. They've got these very frictional walls, and we get these kind of velocity profiles, some shear zone where the shear is quite high, and then this almost plug-like region in the center where the strain rate is really small. And so that, of course, is when the inertial number is really small. The next thing we think, well, due to symmetry here, this is perfectly symmetric, at the midpoint, we have to have the strain rate being precisely 0. Inertial number has to be precisely 0. But the momentum balance also tells us, the force balance tells us, the friction has to be 0 there as well. And so that was looking actually quite similar to what my curve was looking like before. And these red circles are the kind of results from this geometry. And this looks a lot like, I don't know if you remember Nico's talk, he was talking about how static granular material had multi-valued values of the friction. So that looks really similar, except if you take now a log axis. And so all these points that look like they're constant are actually now pushing really against the experimental precision. 10 to the -6, I'm told, is about as good as we can get in these particle simulations with the method we're using. In any case, you can see, even before we get to this limitation, the flow is kind of really creeping. So on the edge of these zones, it isn't a sudden transition to perfectly static, it is creeping very gradually. If it was perfectly static, it would have gone across horizontally here, but it's got this kind of creeping flow behavior. And so just out of interest, earlier today, I plotted on this black curve, which is that neutral stability line from the analysis, and then scaled it a little bit to make it definitely inside the curve and do a bit of fitting. But yeah, it's pretty close to that neutral stability curve. And, you know, maybe there is some physical basis to what we're being told from the analysis. For high inertial numbers, as I said, it looks like the neutral stability curves are all above the classic mu of I curve. And so this was in Manchester. I did some physical experiments of shoot flow with high-speed cameras and lasers and all sorts of nice equipment to try and measure the inertial number at different angles. And the blue dash curve again is the Jopfotet and Poulican kind of gold standard literature result. The blue vertical dash line is where I would expect that theory to go ill-posed, and the black one again is some example of a well-posed curve. So there's this kind of like nice maybe physical connection and physical justification for where this comes from. Okay, so that's the incompressible mu of I rheology kind of done. We're kind of happy with the gains we made with playing around with the shape of that curve, but it all seemed a bit arbitrary, and also it seemed a bit like, yeah, a lot of curve fitting. And also when you actually start looking at different geometries, you find that in those regions, very slow flow, very fast flow, you don't really have this one-to-one relationship between mu and I anymore. In fact, those are the flows when the volume fraction, so the density of the material, really starts to matter. If I've got a fast flow, I'm going to expand, and that should be incorporated in the model. If I've got a very slow flow, I'm going to start getting loads of contacts and loads of frustration by the fact that everything's wanting to pack a lot more closely. And so this other non-dimensional variable now, the volume fraction, so the amount of granular material compared to the total volume, that also turned out to be a nice fit against the inertial number. In this paper that actually came out around the same time as the mu of I guys, there was other people looking at phi of I. And so the idea from us a little bit, but definitely from the community, was to just plug these things together, create a combined mu of I and phi of I rheology, so that mu is always a slave to I, as is phi. But some other guys beat us to it kind of, and we did our own version, but that also turned out to be an ill-posed model. If you just plug these two dependencies together very rigidly, you end up with kind of guaranteed ill-posed equations. And so that was, seemed like a bit of a dead end, but we thought, well, the issue probably is that we're really, when you got mu of I and phi of I, you could just create everything as an I-dependent model or a phi-dependent model. You know, phi and I being so rigidly linked is probably where the downfall comes from. So we decided to kind of consider a much more general framework where the volume fraction, the inertial number, and the pressure are all independent variables which can evolve due to the conservation laws and the balance. But we also needed an extra closure relation now. Because we don't have incompressibility, we don't have div u is equal to 0 anymore. And this is actually something that was being done in soil mechanics and solid mechanics. Like if you've got a building, say, on a sand bed or on soil, the deformations are really slow, right? And so those kind of dynamics are very quasi-static. But what is really key in those scenarios is the volume fraction. As you shear, you're at those slow rates, the kind of particles which are potentially very stiff themselves have to get around each other. As they get around each other, they create voids. So in order to support that shearing, it can kind of expand. Or if it doesn't expand, it creates massive stresses and pressures that can, you know, ruin your foundations or break your grain silo or something. So anyway, we borrowed from that literature to cook up a dilatancy law as well. Again, very general, describing, you know, another kind of key non-dimensional number, the ratio of the divergence of U to the shear stress. Okay, so how much am I compressing or how much am I dilating in time? So we can process those equations in a very similar way. We can assume alignment. This time we're differentiating between the shear stress, the shear strain rate, S, and the full strain rate, D, because we're expecting granular materials are going to differentiate between those in terms of shearing. Deformations are going to be a lot more dissipative than the volumetric ones. And we've already accounted the volumetric ones in our new dilatancy law. In any case, we've got this dilatancy law linking this non-dimensional divergence to our state variables. Let's invert that, and hopefully we've got implicit function theorem and things like that that could hopefully help us for like decide what class of functions, etc. But if we can do that, we can create an equation of state now for the stresses, for the pressure, in terms of how fast I'm dilating or compressing. That will obviously affect the pressure. If I'm pushing things together quite quickly, it should be a larger pressure. The volume fraction, of course, I need some material there to generate the pressure, and the inertial number, which is this non-dimensional strain rate. And so you can process it like this, and you get an equation that looks very similar to the incompressible case for the full stress tensor, where now this y function plays a role of that mu of I times p, and the pressure no longer responds to incompressibility and say gravity or something like that. It's a function then of the kinematic variables. The pressure is a response to shearing, is a response to compression, is a result of density of contacts. So this top green line is kind of summarizing that same process that we used for the incompressible case. I'm not going to focus too much on the details. You know, again, we've still got three variables. Instead of the pressure now, it's the two velocity components and the volume fraction. In fact, we kind of kept the pressure as an extra possible dependency to kind of see how that all filtered through. But in any case, we've been able to do some other trickery, not exactly the same tricks as last time, but to reduce everything again to a single eigenvalue problem in terms of just a velocity perturbation. Okay, so I'll go through these terms one at a time because there's a lot happening here. This first term in the operator acting on the velocity perturbation looks almost identical to how it did in the incompressible case. This is like the base state viscosity, y over so this is like the shear stress over the shear rate. Okay, and so that's kind of like a viscous term, negative. Of course, that's going to be quite dissipative. It's going to kind of quash these modes. And then the next term has got this is scaled by this A factor, which looks very similar to when I had d mu by di. This time I've got dy by di. Okay, so again, it's starting to pull out terms which depend on my choice of these new constitutive functions in terms of the kinematic variables. And then it all came down to this final term. And we looked at this for ages and scratched our head. It was, to start with, really hard to, you know, pull out good factors and to get it in a reasonable form. But it really worried us because it didn't look like we were going to be able to solve this. Well, we're definitely not going to solve it exactly like we did before for the growth rate. And we probably weren't going to be able to know much in general about the sign of the growth rate either. And that's all because this final term was asymmetric. You see these off-diagonal terms up here, it's 1 plus b, 1 minus c. Here it's 1 plus c, 1 minus b. And that asymmetry was quite a hindrance. And so to start with, we thought, what if this extra term coming from compressibility, coming from this new structure, was symmetric? Let's just force it to be symmetric. Let's make b equals to c. So these two terms are symmetric and b equals to c. As we see, both of those groupings of terms, again, are telling me about how I should set my functions. It's got gradients of the yield stress function with respect to p, with respect to I. It's got this new dilatancy function, how it changes with I. And so setting those equal to each other is again a nice recipe. And so we've got now that symmetry condition kind of helping guide everything. Okay.
Sorry, can you just remind me to see the physical significance of B and C?
B and C were just groupings in the like leading order linearization after I took the highest wave number modes. So they're the factors which are going to control the linearized stability.
Where is it different?
Okay, so if they're equal, you have
I know
that.
it's very equal because why is it okay to assume what allows you to do that?
Yeah,
Without actually doing something trivial
The-
and not so useful.
exactly. Yeah. Well, just in this first line, I just want to point out what it means by symmetry, and that is that this linearized operator acts the same on the one component as it does on the two component when you switch your indices around. At first, we kind of thought this could be to do with framing variance, but it's not quite that actually. Like we just went with it and we published it, but then these physicists came and wrote a really insightful paper saying that all we applied by constraining ourselves to this symmetric term was known as on-Saga symmetry. Okay, and so they really like that because thermal systems, when they're on-Saga symmetric, have this kind of really these nice properties. They can be written in yeah. It means they can be written in terms of dissipation potentials, which are convex. It means that you've got positive dissipation rates. So yeah, there's a lot of nice things that have come out of it. We chose to do it for the fact that it made the maths possible for us. But yeah, we're now, we think there are well-posed equations without on-Saga symmetry, but we're not sure yet if granular materials should have on-Saga symmetry or not. It's an open question. A lot of people people coming from theoretical physics are using that as a starting point for developing laws for granular materials. The issue comes from the fact that Lars Onsager, who won the Nobel Prize for his derivation, started off from saying the laws of nature at the point scale are reversible, or time reversible. And then he built up this kind of theory that was at the meso scale and that was about dissipative systems. So we're looking at particles which are banging into each other and undergoing frictional interactions. That's not time reversible. That's the opposite. But yeah, so there's this debate whether or not granular materials should have this symmetry. Okay. So yeah, so that's what we said. Let's just make it symmetric. That gives us a symmetry condition. If we want well-posedness as well, then we need these negative growth rates. So we have this really complicated operator acting on our velocity perturbation. But really what we found is that the determinant of that operator was going to be positive or negative to give us negative growth rates, so long as these two other groupings of dependencies were greater than 0. One of them, I'm still not quite sure how to interpret. It's telling us how this dilatancy function varies with pressure and inertial number. I'm not entirely sure if there's much physical basis to that. The other condition, A greater than 0, is telling me that the shear stress should increase with the inertial number. More shearing should increase with higher, correspond to higher dissipation. And you can also derive the same condition if you say that the product of the full stress tensor with the full strain tensor is greater than 0. So in other words, that is positive dissipation. So these are kind of nice physical properties that popped out when we were looking at the mathematical problem. It's just, I guess, a different perspective and a different set of tools. So just to finish, we cooked up an example of CIDR, our compressible I-dependent rheology. I think the acronym probably came first. Yeah, so we've got freedom of choice of this f and this y function, so long as they satisfy this symmetry and these well-posedness conditions. But that still gives us like infinitely many choices we can make. So we need some kind of boundary conditions, if you will, or like limiting states. And so we say that for steady flows, and when the flows are also isochoric, so there's no volumetric changes happening, then we'll go back to BUI rheology and 5i rheology. So they're the things that have been well experimentally, found. But during transients, anything that is non-steady or non-isochoric, we're of course going to have divergence or contraction. And so delta is going to be non-zero. And so we just cooked some up that had all these nice properties and solved those in a time-dependent problem where we started with some perturbed initial conditions, some sinusoidal function for the velocity, I think it was, at time equals 0, the two velocity components. And we compared that to doing exactly the same procedure in these particle simulations as well. So we got our particle simulation, all the particles shearing, and we then replaced all their velocities with these perturbed forms. And then we watched them relax back to this simple linear shearing, the simple shear box. So at early times, yeah, you've got some perturbation. The volume fraction field is homogeneous at early times and late times. And in between those, you have this evolution. And again, the well-posed constitutive equations did a really good job, and they didn't need any extra fitting parameters to accommodate this extra time dependence. We just had the steady laws. So we had the same parameters as the steady response, but the transient response was set by all these conditions. So yeah, here's the full kind of time evolution of one of the global parameters to show you there's kind of non-trivial structure to how these things evolve sometimes, some kind of ringing and oscillations and all sorts of cool stuff. But the DEM and the theory are not too bad for these systems. So yeah, that's everything. Thank you very much.
Thank you, Tom. I think we have time for one or two questions.
So the whole process is trying to understand which of the BUI functions when they were
Mm-hmm.
Are there any that are always well-posed, or is it always?
For the incompressible situation, as I said, for low inertial numbers, I can do that kind of patching and I can make it work. For the very large inertial numbers, there's always this upper bound that happens at mu is square root 2 somehow in that condition. If you substitute that in, you see straight away that's like, yeah, it
So
ruins the party.
reality kick in?
When does what, sorry?
Where does reality kick in? Because you don't see this a lot. Where does theory and reality part of it?
Yeah, I mean, that's still open research. There's kind of two communities. There's a community that's worked on the inertial flow, and then there's three communities probably. And then there's another that have always worked on gas-like flows that have done these kind of like convection rolls and things of like vibrated beds and all that kind of thing. So yeah, it'd be interesting to see if their theories are just completely different in those limits, but we haven't got that far. They've got a lot more balance laws. They often have granular kinetic energy in part of their balance laws. So they have an energy balance with loads of terms which are semi-empirical, or it gets quite complicated.
So in the work with processes, so they use the principal part of the operator to look at the top of the system.
Yeah.
So just exploring that a bit further. So are there targets of Granular that change the type of the system as high initial numbers?
Yeah, so in the compressible situation, yeah, those conditions are, I guess maybe that's one interpretation of the conditions. It's a loss of hyperbolicity, right? That would also, yeah, that's another way of thinking about ill-posedness of these kind of problems. It's like the hyperbolic parts, yeah, are gone. So yeah.
Okay, I think we have to leave the window, so let's thank Tom again. And we can all go to the common